Okay, you've got a problem where, of course, these vectors are written out with semicolons.
Yeah.
The first thing you want to do when you see this matrix equation or vector thing, anything where you've got semicolons, you write them in columns. You write it out in your paper in columns so you can see what you have.
Okay.
Now, you skipped a step, but you did it right.
Yeah.
Okay? So I'm not going to skip the step. Let's say this is your equation, right?
Mm-hmm.
Okay? So what can we say about this? Well, this is the same as this multiplied by C1, C2, C3. Not because of some magic that when you write these things out as a single matrix, it works, but because that is what works, okay? And you check it out to make sure that, okay, am I going to get C1 times this plus C2 times this plus C3 times this for this number, right?
Mm-hmm.
Well, let's see, we have 2 times C1, so I got C1 times 2, right? And we got negative 3 times C2, so there's my negative 3C2, right? And we got 1 times C3, okay? In the first row, first column of this product, right?
Mm-hmm.
Okay, so well, that's exactly what should go in the, that's exactly what should be equal to the 1, right? C1 times this, C2 times this, plus C3 times this should equal 1, right? So writing it this way makes that happen, and you want to check that out and make sure you've got it right, because you want to make sure you understand what you're doing, okay?
Okay.
Then if you want to know, is it possible for these things to add up to this vector? Okay, well, if this matrix is invertible, it's possible, right? And there are such C1, C2, and C3s, okay? How do you determine if the matrix is invertible? Well, you could write it down, augment it with the identity matrix, and go through the whole process.
Mm-hmm.
Or you could just row reduce the matrix and see if you get a row of zeros, right? Or you could take its determinant. Okay? So there are 3 equivalent conditions. Okay? Now, I'll just do the determinant quickly to make sure it's not 0, because the way just making up these numbers, it's unlikely but not impossible that it could be 0, right? Now, on your paper, some of the problems I made it up so they'd be 0, some problems I made it up so they wouldn't. Okay? Okay, anyhow, you got 15 and 3 is 18, and that gives you 36, right?
Mm-hmm.
And then the negative 3 on this, that's going to be a negative 3 and a negative and a positive 4. That's not going to get close to 36. And this is going to be negative 4 and negative 9. And that's not going to get close. Okay, so I can see right away that's not going to reduce. Okay? So I can say this. Matrix reduces to the identity. Okay? The augmented matrix reduces to give the inverse matrix, right? Well, all 3 of these conditions are saying the same thing. Each of these conditions happens only if and only if the other one does. The other one's do, okay? These are equivalent. Conditions. So you could solve this by reducing a matrix augmented with the identity, right?
Mm-hmm.
Okay, and I didn't really say the matrix augmented with the identity, okay? Reduces to give the inverse anyway. Matrix reduction to reducibility of the identity, determinant's not zero. Matrix is a product of non-trivial elementary matrices. Word non-trivial in parentheses because it's an elementary matrix. It isn't trivial. Trivial means got all zeros. Okay? And incidentally, a question came up, a trivial solution to a homogeneous equation, we got zeros over here. Well, C1, C2, C3 all equal to 0 is always going to give you 0, right? That's the trivial solution. Okay? In some of the questions we ask about a homogeneous equation, we ask about non-trivial solutions. Okay? So let me wrap this up, then I'll address that real quickly because that question already came up. And people who aren't here, I want to see that, right? They're all over there working with our last year's linear algebra students who are probably getting a good workout. Make sense? Okay, so do I understand everything that's the same? And if the question is, does it have a solution? Okay? Then you can answer it like this, okay? Make sense?